several things of note. The usual email list. If you, I mean, most of you know about this meeting somehow, but we do have an email list. We're also on Facebook and YouTube. Yay. Um, if you're not an SBE member, you guys ought to join. It's fun. You know, it helps. It not only does it help national with funds, some of those funds actually come back to us, and therefore you get to eat these sandwiches and salads and a wrap that he has. And then next month,
people think you're smart if you join the SBE.
they will.
They will. At least give them that.
Yeah, it gives the impression that you're smart. And with that being said, not being smart, but joining the SBE next month on the 21st is our holiday party. Please register. Registration closes on the 7th. After that, there won't be enough food for you because they want the numbers by the 7th. And at that party, whatever you want to call it, gathering, we will be drawing every one of you and others who have been here at least twice this year in person. We'll do a drawing to give you guys an SBE Members Plus membership. We'll pay for it, and also consider getting certified back to the SBE national stuff. That's where people think you're smart because you can sign your name, comma, A B C D E F G, just have the whole alphabet after your name, and it makes you look like a genius. Anyways, with that, we're grateful that Jacob has agreed to be here, and I'll hand it over to you. I'll sort of hand it over to you. If I can remember how to do stuff, I'll stop sharing, and I will make you the host.
Uh-oh.
Right? I assume, do you have PowerPoint stuff?
Yeah, I do.
Okay, cool. Then I'll make you the host. Make host. Make host.
That's a lot of faith and a lot of trust.
I know. And we're glad you, John, and Mike, and Steve, who's with Mike, have all joined us remotely. Anyways, I'll hand it over to you.
Awesome. Let me share my screen. Okay, I hope you guys can see that. Let's see here. No, can't see it still. Uh-oh.
Yes, we can see it. Sorry, I don't know how to work buttons and couldn't unmute myself.
Yeah, I was gonna say, I think everybody just went muted there. Okay, there we go. Okay, so as Amanda said, I'm Jacob Daniluck. I'm with Tieline, the Codec company. I'm the VP of sales for the Americas market here at Tieline. We have 2 global offices, one in Perth, Australia, one here in Indianapolis, Indiana, and that's where I reside. Sorry, jumping the gun. Excuse me. Lately, this past year, we've been doing a presentation called All Things Codecs, Troubleshooting Modern Codecs. Because we get asked a ton of questions about how to keep stability of your STL links or your remote broadcast links. So we figured it's always a great idea to refresh on what some of the common occurrences you'll find with like STLs, how to get through some of the troubleshooting issues that you might encounter, audio drops, audio loss, etc. To begin, I am going to kind of summarize some of these things real quickly because I know you guys know it. But as you guys can imagine, I have a broad range of audiences that I have to entertain. Studio to transmitter links, that's what I mean by STL. You're going to have a data input or a media input, your encoder, a transmission medium, a STL decoder or a receiver, and your data output. That's kind of the summary of the on-air data chain, at least going from the studio with your program to the tower to receive the program feed to output it over the air. STL technologies, you'll find there's a wide range of different forms that you can use, RF being one of them. I won't cover too much of RF, but you have like UHF, VHF bands that you can utilize. Some might require a license, some may not, depending on what frequencies you're going to utilize. But it takes power, typically quite a bit of power in comparison to other technologies. And you're going to have a higher maintenance cost typically with an RF based systems. You can also go with like leased or dedicated lines. What I mean by this specifically is like a POTS or an ISDN or a T1 or an E1 circuit specifically. They're typically utilizing what's called circuit switch data for their transmission means, or it's a dedicated point-to-point line. This is typically older technology nowadays. If you're still running a dedicated or at least line setup for your STL, I'd encourage you to look at alternatives because you'll find that there are cheaper, less expensive alternatives out there that can provide you just as good reliability or quality. What I'm going to be focusing on is public or managed IP-based systems, more so. Think of private or public IP or internet connectivity. This does require some sort of data encoding and or compression to transmit your lines. And you'll find this over a wide range of transmission mediums like leased lines, fiber, satellite cable, wireless RF, licensed or unlicensed. We've actually been seeing an uptick in 5.8 gigahertz wireless links lately because not too many people utilize 5.8 gigahertz. So it's great because there's not that much traffic on those bands. With IP systems, you can typically push higher quality audio at a much reduced cost in comparison to like RF or leased lined systems. So you do typically get a big benefit by jumping to an IP-based system. Some of the different types of codecs you'll hear me discuss or that you might encounter would be a hardware codec versus a software codec. A codec is a very generic term because it essentially means to encode and then to decode. Here, when I'm referring to hardware codecs or software codecs, we're talking about audio or video encoding and decoding of said data from point A to point B typically, or there might be a syndication use case in there as well. Hardware-based audio codecs or video codecs, you're going to find that they're typically dedicated appliances. They're not off-the-shelf computers built around trying to do this one purpose. Typically, like companies like Tieline, we design DSP-based systems that are solely designed for this process. So you can have lower power requirements typically with dedicated appliances. Typically, it's going to be more consistent and more predictable performance in comparison to a software-based appliance or running on a PC. We get lower latency audio. They're more rugged and reliable. And typically you have better integration of your audio. Software codecs, you'll find that they're much cheaper, much more, that they're more cost effective typically, just because of that initial upfront cost. I can spin up a audio codec bridge, if you will, running VLC, video LAN specifically, and it's free. It's a free application. But there are nuances with that. One, yes, it's going to have to run on my existing IT infrastructure, and I might have to manage said IT infrastructure. We have, they're typically upgradable, where VLC will push out, like as an example, they'll push out updates, software updates, but you also have operating system updates to worry about. They are typically more adaptable and quicker to market. So VLC, for instance, they pushed out their Opus support back in 2013, a year after Opus came out, as an example. It took Tieline to adopt that 2.5 years after that into a DSP-based system. So it took us a little bit longer to actually integrate that properly. And then with software stuff, you can scale them typically. You can run them in a container or a VM or a cloud-based system, and you can scale them to your heart's content in that aspect. There are cons to both sides. Hardware is typically a higher upfront cost. They're typically not as flexible because it's up to us manufacturers to implement those features for you. There is, of course, a physical footprint, and we're limited by the hardware design, specifically in terms of lifespan. So if Intel pushes out a new FPGA and the old FPGA goes end of life, there that goes for us. We have to adapt and build a new appliance at that point. Cons for servers and software, you'll find that it requires hardware still. That footprint, though, is based off of you, of what your needs are. Consumes typically a CPU and a memory. Under load is typically a little bit higher than a dedicated appliance, so you are going to have more overhead. So you may not be able to scale as highly as you could with like an FPGA platform. But again, FPGAs are hardware-based systems. You have to rely on us manufacturers to do that. Latency can vary greatly with software codecs. We've tested some codecs ourselves via software that have latencies as low as 50 to 100 milliseconds, but we've seen them up to a full second. Now for your STL, this may not matter. When we're talking though remote broadcasting or sports gathering or a talk show that's across multiple studios, latency is going to matter. Even that 50 to 100 milliseconds, that is going to matter. Hardware-based systems, utilizing FPGAs or DSPs, we can see latencies as low as 10 milliseconds on that side of things. So you get a much quicker time to air. So some of the things we're going to go over: coding and decoding techniques, network realities, reliable strategies, hybrid approaches that you can utilize to help maintain and make your STLs more rock solid, control and monitoring of these things. And then we're going to briefly touch on newer technology for IP STLs like MPX over IP, and then a little bit about maintenance and security, which is always a big one because I always hear of horror stories with people and their STLs. So the process for the algorithm aspect is an algorithm overview. Not too many people understand truly what happens when we encode and decode audio. So to give you a brief, quick through of that, essentially there's an A to D converter built into the codec somewhere, and it's going to accept your XLR, your BNCs, AES3. It's going to accept your data source. Then we're going to process said data. And this is going to be dependent on the algorithm itself. So for instance, if we utilize AAC versus Opus, those two do have different processing steps to go through. Some of them offer error concealment, some of them do not. Then after we go through the processing stage, we have to packetize the data. This is typically outside of the algorithm and it's based on the operating system itself. But we have to prepare the data to actually be transmitted across the network itself. Then we have the transmission medium itself, or the IP network transmission. This is the type of network you're running on. Typically, it's an RJ45 IP LAN network going across to WAN that gets converted to fiber or coax, etc. Then once we receive the data, we have to buffer and decode. Due to the nature of an IP packetized network, packets can arrive out of time or out of order, if you will. So we have to prepare the receiver in a way that it knows to wait a certain amount of time to receive that data and then decode said data. Depending on the codec you utilize and the algorithm you utilize will depend on your buffer setting. As I mentioned, Tieline, we can go as low as 10 milliseconds, but we can also go as high as 5 seconds. And the reason why you want an adaptable buffer or a buffer that has a broad range like that is because you don't know what your transmission media's latency could potentially be. We've seen latencies on a fiber network be as low as 4 or 5 milliseconds, if not lower, especially on dark fiber networks going point to point. We can get it down below sub 1 millisecond. However, when we talk about like satellite or Starlink, as an example, a lot of people have been asking us about Starlink usage lately. How does that buffer? How do codecs handle that? It can be done. On the low end, if you're going to a bird and not a ground base station with Starlink, you can have a high delay. Even though Elon will tell you differently that their delays are very low, physics wise says it's going to be a little bit in comparison to like fiber. Our tests have shown that it's at least a bare minimum of a quarter of a second or 250 milliseconds. So you have a quarter of a second over satellite, over Starlink, but then we can have something as low as 5-10 milliseconds over fiber. Again, these times and these latencies might seem like very minuscule because we are talking less than a second. But once you start adding in a quarter of a second in my network delay, plus 15 milliseconds on my encode delayed, and then let's say you now need to jump this into a SMPTE 2110 network or a WheatNet network, et cetera, you could have even more delay depending on those network technologies. So once we start adding up this delay, talk shows or remotes start become more unbearable for the end users or the operators out in the field. But once we receive and buffer it, we do decode it. And again, if there's any air concealment, we'll notice that and we'll process it as needed. And then we'll output the audio via a digital converter. Now, when it does come to your algorithm, you do need to pick the right one for your instance. First off, something to note is about cascading algorithms. You want to avoid this at all costs. If you have a satellite downlink and you're receiving a syndicated show and they're syndicating it to you in MP2, ideally you want to match that algorithm or run uncompressed. You do not want to go MP2 to MP3 and then to AAC. You don't want to jump to different algorithms multiple times over, nor do you want to utilize the same compression method multiple times in a row. Meaning you don't want to take the same audio file, compress it to MP2, take the saved version of that, and then you don't want to recompress that again. You don't want to keep recompressing the same signal because you will start to get artifacting. Some algorithms are more resilient to cascading. As an example, Opus is very good with cascading events, whereas MP2 and MP3 are really poor when it comes to cascading and artifacting. So you want to evaluate your station program. If everything is stored in WAVE or everything is being received in WAVE PCM, you really don't have to worry about cascading because it's all linear. But if you do have your music library in your automation system and everything's stored as AAC, you want to take that into consideration when you're picking your algorithm. You do not want to utilize an algorithm that will provide artifacts into your program material. Latency is another one, as I've talked about already. You got to concern yourself with latencies when it comes to specific links. For STLs, most people don't tend to care. But again, remotes, talk shows, anything where you're affiliating with another studio and there is talkback between the two facilities, you are going to want to care about that latency. You want to consider running lossless if possible. So like uncompressed or enhanced aptX or FLAC as another example for some of our other codec manufacturers out there. You might want to consider running lossless because again, it can help you avoid cascading, and lossless algorithms tend to be very quick on their latencies. And then you want to consider bandwidth stuff. Your bandwidth is a big one. If you don't have a big enough pipeline, you're not going to push your signal at all. Now, specifically, Tieline, we focus on audio. So my next slide is a bandwidth tree of the most popular audio algorithms that are utilized. And this just kind of gives you an idea of what your typical bit rate would be for bandwidth consumption, your codec delay, how long it actually takes us to process the audio and encode it, whether it's lossless or lossy, and then just some generic notes. And again, this is just audio-based stuff. Video, you'll typically find is double, if not triple, these bandwidths requirements. And in some cases, it's 5x what we need. So audio, we need a very little amount. Video, you need a lot more. That's why you'll find like And with video encoders, you'll find that they can typically support 3, 4, or sometimes upwards of 8, like wireless cellular modules. Whereas in the world of audio, like for Tieline as an example, we can accept up to 7 interfaces, but we always tell you, you really just need 2. And 2 is even a push depending on your use case. So it's just something to keep in mind is about bandwidth, latency, and picking the right algorithm for you. When it comes to bandwidth consumptions, you want to, depending on your market, where you are, etc., most ISPs are not metered, meaning you don't have to worry about it. You can push as much data through their network as possible. Whereas like wireless ISPs typically around the country, right now they're unlimited, but they're only unlimited up to so much data consumed. So for instance, AT&T, they have an unlimited account. You can get it unlimited up to 30 gigs. Once you hit 30 gigs, it's still quote unquote unlimited, but they will start to throttle your speed. That's something very important to know about. If you're running a wireless carrier right now and you're having problems near the end of your billing cycle and you're having audio drops or audio glitches, it's probably a metered connection, and you've probably gone past that first threshold with your carrier, and now you're in that unknown territory of how much bandwidth are they actually going to give you per second. So knowing that is very important. The other thing to note, because we're asked this all the time, is my codec is running 256 kilobits per second, but AT&T says I have 10 gigabytes. What's the difference here? We should all, I would hope most of us would know it, but it's always a good reminder, there is a difference of 8. So if I'm running 256 kilobits per second, in terms of consumption, you're looking at a difference of 8. So you're looking at 32 kilobytes of data consumed there, and that is per second. So that can add up, but there is a difference there that we have to keep in mind. So bits is how much speed we are pushing through the network at once, but your bytes is how your ISP will measure how much data you've sent through their network. So there is an important difference there. In case anybody is curious about calculating your bit rates or your bytes, here's a quick little algebraic equation that you can look at. There is one important thing to note, even though we'll tell you, let's say again, you're streaming at 256 kilobits per second, you're really not. There is an overhead. There's always an overhead. The overhead is dependent on what algorithm you're running. So AAC has a higher overhead than MP2. So that is something to keep in mind. Or like PCM linear tends to actually have the highest overhead in comparison to everything else. As a rule of thumb, here at Tieline, we've always said just add 20%. If you don't want to go through our manual or go through the research of figuring out how much overhead AAC should be, because there is a couple of equations you can calculate to figure that out. A rule of thumb, without getting super advanced, is just add 20%. So if it's 256 kilobits per second, add in or add 1.2 or times it by 1.2, and you're roughly about 308 kilobits per second. So that is something else to keep in mind, that even though your bit rate says one thing, your speed required is actually a little bit higher than that. Let's see here if I can click correctly. So some network realities to worry about. If you're worried about time, algorithms can matter quite a bit, as I've mentioned once before. If it's an STL, you may not care. So again, run linear, run enhanced aptX, run whatever algorithm you want. Time won't be that big of an issue in terms of getting the signal there. Now, depending on your network, you have inherited network jitter that we talked about briefly. And that is due to the packet-based system of IP as a whole. So we have to give enough time to decode and receive that audio. And then when it comes to STLs, especially like SFNs or MFNs, now you're starting to get into synchronization across multiple receivers. And that's where you are going to have to start worrying about like satellite GPS, PTP, or NTP synchronization styles. And that's just using a master clock, if you will, somewhere on your network or somewhere that you have access to specifically. Here at Tieline, we work with PTP and NTP at the moment, but our hardware is already ready to accept a satellite GPS sync. We just need to do the software aspect of it. Shared environments. So we run across different network types all the time. The most common one is people love to just put broadcast equipment right onto a shared network, like their office network. There's nothing inherently wrong with that, but you could notice a few little quirks along the way. One, shared network environments means you have shared bandwidth. Even though you paid, let's say, for a gigabit up and down with AT&T, but your internal switch is only a 100 meg switch, you will be limited to 100 megs. And that is for everything in your office. So your least common denominator network equipment is going to determine your network shared bandwidth specifically. So that is a key difference there. The other thing to keep in mind is typically when you have these shared network environments, you really should be implementing like quality of service on your network. QoS is extremely important to set up. It helps prioritize the bandwidth that is allocated inside the network. QoS does not work across the public internet, but by all means, it can work internally on your internal network. So if you are running a shared environment, set up QoS. Even if you're not setting up or running a shared environment, still consider QoS just to help maintain and give assurances to yourself that my codecs or my STLs do have the proper amount of bandwidth required. In addition, segmenting networks. If you are in a shared environment, I still strongly encourage you to consider segmenting your network. If you aren't in a position to get more hardware to physically isolate everything, consider VLANs. VLANs can still segment some of your network devices out there. It provides a little bit of additional security, but it can also reduce the amount of bandwidth noise on each network segment, specifically in the broadcast realm on the IP network. Security realities, firewalls help keep the public out of your network. And that is very critical. Remember your firewalls and keep them in play. A lot of people we have found, they love to just put their STLs on the public internet on a DMZ. I will tell you this now, our support team is at the point where if they catch you with a codec outside on a DMZ, they're not going to be happy. Our own support team won't, because they will run through the same list I'm going to run through. It is extremely insecure. You are opening yourself up to an attack, and it is a huge potential vector for hackers. In fact, I think it was, maybe a month ago or so, there was another station, I think it was the Faith Radio Network. They had a barracks hack. One of their barracks got hacked and somebody sent malicious audio across their entire STL chain. That does not look good for the stations. And that is most likely due to a couple of things. One, the barracks was probably on the open internet, no firewall. And two, I do know for a fact, they did not change their default password. So if you're going to take anything away from this presentation, at least that. Change your default passwords and keep a firewall in play. Don't go that route. That's all I will say about firewalls. NATing is the core for a lot of private networks and public networks because of how just the nature of everything works. So you are going to have to configure destination NATs or port forwards on your network, especially if you utilize a firewall. And again, if you do want to bypass NATing and or bypass a firewall, if you will, loosely, VPNs. In fact, Chris and Amanda, I think you guys run all your SDLs over VPNs, if memory serves. If my memory is correct there, so don't quote me on that, ask them later. But that's just as an example there. That is a much better way, more secure way, and now you don't have to worry about all of these potential risks that you could set yourself up for. Now getting into how to repair some things. So when it comes to at least the world of audio and video, you can get audio drops, video glitches, audio glitches, a static image sometimes. Those are typically decode issues or data receive issues. The first way to handle this is typically with forward error correction. Forward error correction is just simply taking your data that you have, duplicating it, and sending it again in some fashion. Typically, it is some percentage of your overall data string. So we might take 20% of your data and send it again, or we might take a third of it or half of it and resend it. We're typically not sending the full data package a second time. The reason for this is because it still can allow some error recovery at the other end without sending everything again. Not every algorithm, though, does support this. So like H.264 for the video world, talking about that does have forward error correction capabilities. Opus in the audio world has error recovery methods, even with forward error correction. AAC does, but like as an example, MP2 does, but it's a very poor implementation, in at least my opinion. So not every FEC is created equally as well, and that's why you'll find some are better than others. But it is still up to the manufacturer or the coder at the end of the day to implement it properly. Adaptive buffering. So whenever you start to see stuttering in your audio or in your video, or it's skipping frames, this is typically a buffer issue, just simply meaning that there's not enough buffer typically. So in the world of having an adaptive buffer, this allows us the ability to intelligently try to figure out what is the average latency of the network link. And then can we raise our buffer a little bit higher than that to allow for that data to come through as needed. It does depend on the algorithm. The more lossless it becomes, like linear or enhanced aptX or FLAC, those tend to have a very high packet count, meaning that we can't do much buffering or not as much. Whereas AAC and Opus have a very low amount. So we're actually able to push in about 5x the amount of buffer. Difference here is we can buffer up to about a second for linear or about up to 5 seconds for compressed audio. But adaptive buffers can help with this kind of stuttering or dropping of frames or skipping of frames here and there, just by extending the amount of time. And the reason we have to do this is because, again, inherently in the IP realm, we're sending our data packets through your provider, and they're all going to come out of order. So we have to realign them, but we also have to give enough time for each packet to go through its hop individually. If a server along the way is a little bogged down because, let's say, the Super Bowl's going on and a lot of people are going to Twitter, but you're going through the same server as the rest of your city, that server might be bogged down and it might just need an extra couple of milliseconds to process your data. So having an adaptive buffer can help you try to compensate for that lost time. Adaptive bit rates. So when it comes to congestion or flat out losing data consistently, this typically is a congestion issue. And that's where forward error correction could fix the problem, or adaptive bit rates could. Adaptive bit rates would just simply mean the idea of going from 256 kilobits down to 192 when we sense congestion. Some algorithms have this inherently built in, like Opus and 264 do. But then if we look at like MP2 as an example, this does not have this natively built in. Manufacturers, though, have decided to build this into their hardware and software platforms. And it is more of a notable mention from Tieline, or from my perspective, because Tieline actually does not believe in implementing this function for just the sheer fact that when you do an adaptive bitrate, you do lose audio. When we have to make that adjustment from 256K down to 192K, there is a split second, and it's less than about a quarter of a second of dead air. And here at Tieline, we just don't like that. So we've opted not to do adaptive bit rates. But it is something to mention because it is a useful tool when you do have access to it. So the best way to overcome issues, as I mentioned, how like live view as an example in the TV world can have typically up to 8 wireless interfaces. Here at Tieline, we can have 7 plugged in or utilize up to 2 at once. The idea here is redundancy, redundancy, and redundancy. More is better. It always is. If you are capable of getting different types of carriers to your facility, you can typically leverage both of those carriers and leverage them for better recovery to your tower site or for your remote or whatever you happen to need to get transmitted from A to B. The idea here is what we call hitless packet switching, or some of you might also maybe know it by SMPTE 2022-7 on the video world, but this is that's more for video and audio streaming inside of a private network. Hitless packet switching is taking that to the world of a WAN across the public internet link. And it's more adaptive or adaptable with higher latencies, more congestion, etc. So what we're doing is sending data across both networks simultaneously at 100%. So it is a duplicate feed. And the idea is as long as we take 2 different paths to the same destination, we can have a little bit more recovery there. You can also do things like time offsets with these Smart Stream Pluses or hitless packet switching or crosslock technologies, where you're sending everything at a delay. So instead of having 2 networks, you might only have 1, but we can send your primary signal in real time, but then we can send a backup signal maybe at a half a second delay. And the idea here is instead of going across 2 different networks, we're going across 1 network. But as I was talking about earlier, let's say you have a server bogged down. Well, maybe you might be bogged down in that split millisecond, but 50 milliseconds later, when your next packet, your redundant packet comes in, it may not be bogged down. So we're trying to bank on the idea that servers aren't under load with a time offset. You can also do things like network bonding or network, like a network round robin, if you will, where you may not necessarily have enough network resources to push the signal quality you are looking for, but you might have enough network resources in terms of different ISPs to be able to push it across to all of them. So you can always do network bonding. That does have some inherent forward error correction built in. And then, as I mentioned, manufacturers were all starting to implement these kinds of technologies to help make things more reliable for our customers out there. But now getting into MPX, the next generation of modern STLs, at least in our opinion. So I'm sure some of you guys have seen charts like this. Just to recap, when I'm talking about an FM MPX signal here, is I'm talking about a FM composite signal where you have your L plus R For mono, your 19 kilohertz pilot, your L minus R, RDS, and SCA. And sorry, any TV guys here, I am talking specifically FM at this point. So that's what I mean by MPX. So before, you would typically have your IPSTL or your 950 link or your leased line or your dry line connection, sending the audio main program through a processor maybe at the studio and sending it out to the tower. And then at the tower, you're receiving your program, you're processing it again, maybe you're feeding your RDS encoder, and all of that combines to your single output for your tower, for your exciter. That's one way to do it, and it does work. But now we also have resources away from your main studio. So that might be more time outside the studio in case something happens to, let's say, your RDS encoder or your FM processor out at the tower site. That can now require an on-site visit. And I know some of you guys have towers that are very close to your main studio, but I also know some of you guys have towers that are on top of mountains, hours away from your studios. So you have to worry about those instances. With a newer IP-based MPX system, you're backhauling your FM processing to the studio, you're backhauling your RDS encoding to the studio. You're doing everything back to the studio now, more or less. We're feeding a composite, excuse me. We're feeding a composite AES 192 or analog signal into your codec, if you will, streaming it at a sample rate of 192 kilohertz in linear, uncompressed, or there are compressed versions that can do this. And we're outputting a raw, uncompressed composite signal for your tower or an AES 192 signal for your tower or your transmitter at that point. That's the idea of an MPX codec. It keeps the composite chain at the studio instead of at the tower site. So it helps move that OpEx resource or expenditure of maintenance back to the studio. So it's less time on the road. It's great for centralization of programming because now you don't have to worry about needing, if you have a network of 10 tower sites and let's say 4 of them or 5 of them are translators and a few of them are repeaters, you might need a FM processor at each site. So now that's more equipment to manage, where now I can simply backhaul all of that back to the studio. It reduces the configuration differences between sites or quality differences between different sites, because now we're able to, again, centralize that processing. So everything will sound unified across the entire network. And that's kind of the big picture with MPX. Now, I did talk about how there are compressed ways of doing MPX, because typically it's a linear feed. It's sampled at 192 kilohertz and it's either 16 bits or 24 bits. There are some companies here, I've mentioned one algorithm, micro MPX, or for the layman typing on a keyboard and they don't want to have to use Alt 0192 to get the micro sign, UMPX is the other way to say it. It's a compressed equivalent of baseband audio like AAC or Opus, etc. It is sampled at 192 kilohertz. It does have a frequency throughput of 0 to 96 kilohertz frequency response, so that is perfect for an MPX composite signal. And it can reduce the bandwidth roughly 2 to 3 megabits down to about 300 to about 900 kilobits per second. So we are talking a drastic compression ratio difference between linear and micro MPX. The nice thing though, it is lossy, but it is non-perceptual, meaning that the waveform preserves the audio or the composite signal itself, and any artifacting that does occur gets shifted to frequencies that broadcasters we don't care about. Like for instance, talking to the guys at Stereo Tools who wrote micro MPX, a lot of those frequencies are shifted between 16 and 18 kilohertz, right in a frequency range that we just don't care about as broadcasters. So compression for MPX can be very valuable. It makes it more obtainable for most people because now you don't need dedicated fiber links. You don't need dedicated wireless links that have huge pipelines. You can now, in theory, push one of these over a DSL line if you have the right kind of VDSL connection. So it makes it more obtainable. Differences you're going to find between processing at the studio versus processing at the tower. As I kind of mentioned, consistency is one, where processing at the tower, everything is always localized. One central processor, easier for maintenance versus avoiding the full MPX transport bandwidth. So you don't have to have as big of a pipeline when you're running just a traditional audio codec. Easier RDS injection versus site processors need to be adapted for each transmitter needs and requirements for that area. Lower equipment costs for MPX because you're not having to purchase that many RDS encoders or that many FM processors. You typically just need now one per program signal versus beforehand you needed one per tower site typically. So that's kind of the overall idea with MPX. Last but not least, management. Codec manufacturers, whether we're hardware or software, will always give you a way to monitor things because these are considered mission critical links. So you want to be able to know about early fault detection or dead air events or packet loss events. You want to know these things. So there are things like SNNP or VSNNP, depending on where you come from and what kind of area you're looking at. But it's a great tool for monitoring data. You can monitor things like the packet data, how much packets were received and sent on each side. Do those numbers add up? You can see if they're connected or disconnected. You can actually see audio quality. You can see a lot of these options that codec manufacturers provide. And just about all of us provide SNNP. And that's why I call it the simple but powerful network management tool. Made in the 70s and the 80s, and us broadcasters finally caught up in the early 2000s with it. So I'm glad to see that we're moving this way, and I'm glad to see that it's still leveraged and used today. Web servers are another great way. If you don't want to take the time and set up SNNP traps and management systems, make sure you at least have a means of remote control to your product or to your service or solution that you've integrated. Most codec manufacturers these days will give you a web server, especially in the event that they don't give you a front panel. Here at Tieline, we'll give you both because front panels, I don't care what manufacturers tell you, we'll tell you they cost less than like $10 to add on to the hardware. Front panels are very cheap, but it's important to have that kind of access because you may not always have remote access, or like in the event of an STL, one of these codecs is going to live at your tower. You're going to want a way to access that. You're going to need it. These services, though, do come with their own inherent risks. Typically, that is for accessing those sites. If you're not going over a VPN and you're having to go over the public internet, you're going to have to expose what are ports 80 or 8080 or 443 or some variant of over your firewall. Be cautious. Change your default passwords. That is specifically how that barracks was hacked that we were talking about. I'm actually looking at the article now. They just left port 80 wide open and they kept the password default. So I'd be cautious about that. And my last mention here is about web server passwords. Change them. Definitely change them. If you want to see how scary that can be, about not changing your passwords. There's a fantastic website that I encourage each and every single one of you. I'm actually going to pull it up here too, just to show you guys. Are you guys able to see my web browser here? Yes, perfect. So this is a website called showdan.io. We're just going to search the word Tieline here as an example. So here is a customer in the UK. They have their Tieline exposed, or at least that's how Shodan is reporting it. Here's another one from Rogers Communications up in Canada. Here's their IP address, and this I can confirm, this IP for sure. I can confirm that is a Tieline device because I actually know who this customer is. So these are just exposed Tieline products that aren't behind a firewall. And if you're worried about that, let's see here. What's another fun, a fun manufacturer we can all do together? Let's see. Sorry, I don't want to pull up something that's not gonna pull up. Nautel. How many of you have Nautel transmitters? Well, here's a lot of different Nautels out there in the world. And the list just goes on and on and on. I can actually, oh, sorry, see, I need an account. Shodan has a means where I can script this, pull all of these IP addresses into a single Excel spreadsheet, and then I can then program a separate script to start going and pinging all these sites. This is what hackers do. They have a Google search engine for products. So if you're not concerned about your network, like, nobody will find our IPs, nobody's going to worry about this or that, et cetera. They don't need to find your IP. They just need to know us manufacturers and how to Google, more or less. That's all they have to do. So please be security conscious with your devices and what is truly exposed across the network. And if you're really that worried, proxy anything and everything that you can. If you have the means to proxy data across your network to have a single output exposure point, do it. If not, some of us manufacturers have our own proxying methods. For instance, Tieline, we do, where you don't have to expose anything in terms of management wise across the internet. We will proxy all of that data to your PC if you choose to. These, though, typically these kinds of services, because they are paid servers, typically do come at a cost. So that's just something to keep in mind. And again, back to the last but not least, again, redundancy. Again, I'm going to bring this up more times than people really like me to. It is very critical to consider redundancy nowadays. ISPs are very inexpensive in comparison to what they once were. You don't have to have 2 fiber connections. They don't need to both be a single gigabit line. For instance, here at Tieline, I have 4 ISPs. One of them is a gigabit throughput for our office and all of our testing. The others are all less than 100 megs. They are not big pipelines at all. We've done load balancing here, but we've also done redundancy links as well. So that way our uptime is near 100%. Getting to 100% is quite challenging, but getting even closer to it is actually very affordable. It is very doable. You don't have to sign SLA agreements with your ISPs. It's just a matter of micromanaging all of them yourselves or plugging them directly into products like Tielines or other devices that support redundancy methods to do the heavy lifting for you. Some other just quick notable mentions. For those not doing audio codecs or compression, there are other ways to accomplish like an STL link. You can send AES 67 or SMPTE 2110 across a fiber internet link provided by AT&T. Typically, you're going to want a dedicated link or a dark fiber link or an MPLS link to do this. Bandwidth concerns are much higher, and latency needs to be much tighter with these protocols. So if you're trying to stream like WeetNet IP or AES67 across a wireless link, if you don't have the latencies just right, it may not work properly. If you don't have enough bandwidth and you're pushing too many audio streams or video streams over that one IP network channel, you may have issues. So audio over IP or video over IP, in the sense of like SMPTE 2110 or AES 67, definitely doable, but it does come at a higher cost of needing something more dedicated for that purpose. Using RF signals, as I mentioned, they are consistent, they are very reliable. You don't have to worry about third parties typically in managing and performing maintenance. However, though, you might need line of sight depending on what frequency you're on. You're going to have limited bandwidth, and your maintenance cost, though your specific maintenance cost could go up for maintaining that link. But always a good, again, notable mention. So what's next for codecs and compression codecs? More software codecs. You're going to see a lot more of that over the next coming years. Or higher density codecs where we can do more in a single package. And the reason why software codecs more so is because CPUs are finally getting to a much better point where we can do lower latency links over them or push higher throughput links or compression algorithms through them in a means and fashions that we want. They're typically going to be more efficient as well. And again, higher density is just from the sheer fact that Intel and AMD and Micron, Broadcom, all of the FPGA manufacturers in the world, their products are getting very fast, very quick, and extremely efficient nowadays. So we're going to be able to do a lot more scalability with a lot of applicated or appliance-driven codecs or even software-driven codecs. So those are the two big things to look for. So last but not least, best practices or takeaways, if you will, from this. Always test prior to making any trips to anywhere. Place all hardware, especially your mission critical links, behind firewalls. And again, I will not iterate that. I cannot iterate that enough. Expose only what you have to on your firewall. Don't be like some of the customers that we've all heard about or some of the radio stations we've all heard about through the trades that have been hacked. I'd hate for any of you guys to be the next ones because we all forgot to turn something off on our firewall, or we all exposed something we shouldn't have on the firewall. Choose the best codec algorithm for your application in your environment. Just because your neighbors are running linear uncompressed does not mean you have to run linear uncompressed. I understand we're competitors by nature and we want to be able to do a one-for-one quality comparison between them, and we want to match quality. But if your automation system, everything is set up in MP2, linear is great, but if your bandwidth to the tower or your bandwidth for your inbound remote can't accept an MP2 stream because there's just not enough to go around, don't try to force it. Just adapt and pivot to another codec that will sound just as good, but maybe at a reduced bandwidth or a reduced load on your network. Plan for redundancies and alternative medium. Always have a backup plan ready to go. If you currently have a 950 STL and you're planning on switching to an IP-based STL, keep both if you can. Don't get rid of one just because you're upgrading the other. Utilize those backups the best you can. Having redundancy, not just for your IP codec, is great, but also having a backup plan that is over a purely different medium is always good to have. And plan for your data consumptions. If you're running, like again, a wireless remote, or an STL that's on a metered connection, plan accordingly for it. You'd be surprised how much data somebody can push through a network. I mean, if you're running 256 kilobits and you times that by 60 to say 256 kilobits over a minute, it turns into 15,360 kilobits per minute. Times that again by another 60 to take that to an hour, we're under almost a full meg. Times that again, or sorry, almost close to a gigabit of throughput. Times that again by a single day, we're over a gigabit. Take that to a full month, we're at a lot of data consumed. So plan accordingly with your metered connections. Do the math. If you need help with the math, all of us codec manufacturers, audio and video, we all have data calculators to help you calculate how much consumption you will be going through, because this is a real world problem that I have hundreds of customers call me throughout the year complaining that last month I only used 20 gigs. This month I'm used 30 gigs. Well, what has happened? What is different? Oh, I changed my algorithm. Well, that could do it. Making simple setting changes can triple the amount of bandwidth if you aren't familiar with all of those settings. So with that, I'm Jacob Daniluck from Tieline, and I would be happy to take any questions or comments if anybody has anything.
Hey, Jacob.
I got a couple of questions here.
Okay.
I can wait on whoever that was. Who was that?
I think that was Mike.
Mike?
No, go ahead, Chris. You might have the
Mike.
same question.
Well, first of all, tell Steve to wake up. And everybody else,
I'm
all
here.
of Mike's passwords are PASSW0RD.
Oh,
So,
perfect.
Yeah.
Hey,
All of
Chris,
them.
you got an IP address for me?
Yeah. It's BR549. All right. I got a couple of quick questions here. In your experience, what algorithms play well with the HDC codec? And which ones don't? Maybe that's the better question. Which ones don't?
With AAC specifically?
With
Or-
HDC, HD.
Oh, okay. I would say avoid MP2 and MP3, in my opinion. They're both legacy algorithms. Opus is actually pretty good with not cascading and not running into issues. However, though, we define it here at Tieline as more of a remote codec. Great for remote broadcasting. STL wise, we always say it is a subjective thing. Audio quality is always subjective. So try it out yourself, but that would be a good one to look at. The AAC algorithms, and when I say algorithms, there's like 20 different versions of AAC. The ones that come to mind immediately would like be AAC low compression. Some people just call that AAC. Some people call that AAC LC. Some call it LC-AAC. There's like 20 different names just for that one variant. The other good one would be if latency is an issue, look at what's called ELD AAC, which is stands for extended low delay AAC. It has the same compression qualities as the AAC LC version, but it is at, I think, like a fourth of the latency time that AAC LC takes. So that would be a good one to look at as well.
Well, anybody that's running HD doesn't care about latency, so that doesn't really matter. Which of the algorithms that you guys offer have forward error correction? I know they don't all.
Correct. So we've implemented forward error correction in 3 different ways, technically. One is through the inherent algorithmic error concealment and forward error correction that you actually wouldn't have control of. It's just inherently there. Opus supports that, and AAC LC supports that in a Tieline world. For a managed forward error correction where you can set and dictate, am I going to run it at 20%, 33%, 50, or 100%? We've only done that specific version inherently in our session in our protocols or our algorithms. So like the Tieline Music and Music Plus, that's where we've done that. The third way we've implemented FEC is more in a standardized sense, but this now falls outside of the scope of Tieline session, and it actually moves into the open standard SIP. So when running in SIP mode with Tieline, any algorithm we offer can also offer forward error correction. And we offer 2 types of forward error corrections in that, and they're both different RFC standards, but they both accomplish the same thing. So you could run MP2, MP3, any of the AACs, enhanced aptX, even linear, using forward error correction. The big difference though is you can't run it in what we call a Tieline session mode. You have to switch it to our EBU SIP mode. Once you do that, it's still point-to-point audio. You still get our relays, you still get all of our metadata and all of that, but it's just now running over a SIP format instead.
All right. Well, when we're setting these things up, and we have to choose a bit rate and a packet size sometimes, is there a point of diminishing returns for, say, a broadcast STL application where going to a higher bit rate would not produce any further improvement?
Yes, there is. It depends on the algorithm. They all have their own different bit rates to have that concern. The 2 that are off the top of my head that I know about for a fact, without having to go and look it up, would be the Tieline Music and Music Plus algorithms. And they're both, and the rule of thumb is essentially 24 kilobits per channel. Running the music algorithm, when you switch to Music Plus, it's double that. So it's 48 kilobits per channel. So for a mono, 24 kilobits should be the lowest you can achieve to get 15 kilohertz FM broadcast quality. Music Plus, take that to 48 kilohertz or 48 kilobits, and that will get you up to 20 kilohertz throughput. Anything above that, and we'll let you go to 256 on those. Anything above that is not going to give you any higher in or like higher frequencies or lower frequencies. It's not going to do anything beneficial in that aspect, nor is it going to broaden that range anymore. It's still going to keep it at 256. All it's going to do is just clean up the signal a little bit more. But most people don't really notice it. I would say maybe the room you guys are in with everybody there, I'm sure if I played you guys a couple of sample differences and we kept repeating them, you might hear a few differences. But now you go do the same thing with listeners, doubtful. I am so doubtful they'd be able to spot the difference between a 96 kilobit link versus a 128 kilobit link. I doubt most people would be able to spot that difference unless you're trained in that area.
All right, that's all I had.
So Jacob, my question for you was, can you speak a little bit to the discontinuation of support for the Gen 1 Tieline stuff? What does that mean for people like us who use the Bridget ITs and the Bridget Extras?
Yeah, so thank you for clarifying that the Bridgets were it. Bridgets are actually, most people don't know this, that's actually our Generation 4 product, technically. But it would be the first generation Bridget product. Yes, it is unfortunate that we've had to discontinue support and service on those. One, we've been very low on parts for, like the past 9 months or so. We've been relatively low on spare parts. Service wise and support wise, it was just one of those things that unfortunately we do have to move on at some point. With that said, though, the way we are handling our support for our discontinued products, because all of our products are still backwards compatible with each other, is if you have, like, let's say a Tieline Gateway, our new product, or a Tieline Merlin or a Genie or a Via that is still quote unquote in service and in support, if you need to connect your Gen 1 Bridget to a Merlin, you can pick up the phone and still call us. we're just going to view it as a Merlin question or a gateway question or a VIA support issue. You call us in though about two Bridgets needing to connect to one another, our support team is not going to immediately dismiss you by any means. We're just going to simply refer to you to our website and we will show you what specific document you do need to look at. Or we will still tell you, hey, here on this page of the Bridget, you're going to find exactly what you need. So you're just going to see a little difference. We're not going to necessarily walk you through every single menu step, but you are still going to get the information you need. Whereas you call us in about a newer product or VIA, etc., we'll still give you those same resources. We'll tell you, hey, it's on this page if you're a do-it-yourselfer, but we'll also still be willing to walk you through it. So that's kind of where we stand on the Gen 1 Bridgets, but that's also true about what we call our G3 products, like the Commanders, the iMixes, and the older field units of ours. Excuse me, I'm getting the hiccups.
The firmware updates are done though.
Yeah, in terms of the Bridget, I'm trying to remember when the last one was. It's been a minute since we've done a Bridget Gen 1 firmware update. If we were to do one, it would be security driven specifically. And it would be more something like, oh, the internal SSL certificate for the codec has expired and we need to push out a new one to our customers, or else this, and this will break. So that's the kind of thing you would probably run into. But even then, sorry, I'm trying to actually to get to the last firmware build page here real quick to tell you when that came in. But that would be kind of the experience you would get with that aspect of things. Let's see here, firmware wise. Excuse me. Yeah, so the last Bridget firmware that came out would have been 23. So June of 2023 was the last time we pushed a firmware update. And in fact, that was to handle with connectivity resiliency, SIP resiliency, and there was, according to my internal notes, there was a security flaw that was addressed in that firmware build. So if you're not running the latest firmware, it should have a build date of about June of 23. I would definitely encourage you to update it, and it is still on our website. So you can still obtain the firmware and you can still download it and update it.
Anybody in here have any questions?
That doesn't affect the VIA, does it?
No. But VIA would be a little different in that aspect. In fact, VIA has not been discontinued or discontinuation of service or support. In fact, I think the last firmware update for the VIA was, sorry, I might have a weird look on my face. I'm trying to think. I think it was like May of this year, give or take, right after NAB, give or take. And I know we're expecting a new one in the next few months as well. In fact, if you are a Tieline customer, be warned now, our default password is changing. So if it is still password, I'm telling you now, change it before you update, because after you update, if you're doing it remotely, you will lose access. You will have to drive to that site and get the password off the front panel. We are changing it to a random set of 16 characters based off your serial number. So every codec will be unique in that aspect. If the password has been changed, we will not overwrite said password. So you can at least rest assured on that if it's not password, even if it's password 1, better than nothing, we won't change that. Now, if you do set it back to factory defaults after you update it, yeah, you're going to have that problem that it is now the default password, and that default password is no longer password. So just be warned about that now. We are trying, as I'm doing all these SBE meetings, that's one of my notes my marketing team has told me to say. Every show I've been going to, my marketing team is like, remind people. We're pushing out newsletters like none other. We are very worried that this is going to cause a lot of issues, but we are doing this for the greater good. And our thought is we just got to rip the Band-Aid. But before we rip the Band-Aid, I've been told to preach about it to anybody and everybody who would listen. So be warned now.
All right. Well, thank you so much, Jacob. We really appreciate it.
No worries. Happy to join.